for this session is data streams with bounded deletions by Rajesh, Jayaram, and David Woodruff, and Rajesh is going to give that talk.
Hello, everyone. Today I'm going to tell you about data streams with bounded deletions. I'm Raj, and this is a joint work with David Woodruff. So I'm going to begin by talking about where data streams show up, the type of data streams that we're talking about, and where the applications are. So the data stream model is a model of computation that's useful whenever the quantity of data and the amount of data and the throughput of it is too large to store all the data in order to compute functions on it. So instances of this is large IP networks, financial transaction data, large sensor networks where you have a bunch of distributed sensors out in some field and they're sending frequently messages to some central node. And there's many applications and databases as well that I can talk about at the poster session if anyone's interested. So we'll begin by formalizing the model. It looks like this is a little bit off. Oh, well, we'll just deal with it. So the model formally is we start with a vector, a very large vector in Rn. We call this vector f for the frequency vector. And at the beginning of the stream, the vector is initialized to 0. And then, OK, this is going to need to be fixed. Why is it doing this? Here. Where is presentation mode? Oh, there we go. OK, cool. So at the beginning, the frequency vector is initialized to 0. And then throughout the stream, we receive coordinate-wise updates to the coordinates of the stream of the form it, some coordinate of the vector, and then delta t, which is some increment to the value of that coordinate. So there's two natural models that you can look at and that are looked at in the literature. The first is the insertion-only model. So this is when we restrict the values of delta t to be strictly positive integers. A positive update is like an insertion to the underlying coordinate. And then the natural generalization is where we also allow deletions to the underlying coordinates of the stream. Note in both cases, we require that these increments are upper bounded by some quantity big M. Big M and little m, where little m is the length of the stream, these are both required to be, well, we make the common assumption that both of these are polynomials in the size of the vector. Now this is a common assumption. It's not entirely necessary, and almost all work can do without it, but this just simplifies things quite a bit. So the goal of problems in the streaming model is to compute functions of the frequency vector f, but you don't want to store the entire vector f. You want to store some very small, ideally logarithmic in n, sketch of the vector, and then use it to approximately answer queries about the vector f. So for an instance of an approximate query would be to approximate the value of the L1 vector of f. That's just the sum of the absolute values. So in addition to that, I'm going to, first I'm going to show you just visually what this looks like. So you have some very, very large vector, larger than that probably, but this is just for illustration purposes. At the beginning, it's all 0. And then the stream begins, and we receive some updates. And then we receive some more updates and some more updates. As you can see, there's been some negative updates in the stream. This means that this is a turnstile stream, not an insertion-only stream. And then we continue to receive updates until the end of the stream at time t equals m. And at this point, we have some final frequency vector f, and then we want to ask some questions about it. Like, for instance, what is the LP norm of the stream? That's the sum of the absolute values of the coordinates raised to the pth power. So some of the most well-studied streaming problems I'm going to talk about now, I would say probably the most well-studied streaming problem is the heavy hitters problem. This is also known as like finding frequent items, elephant queries. Just the goal is to find the coordinates in the stream that constitute the most significant fraction of the entire mass of the stream by however you want to define mass. So what's one way of defining that? Well, the first one is the L1 guarantee. So that's you want to return all the coordinates of the stream that that constitute at least an epsilon fraction of the L1 mass of the stream. And the L2 guarantee similarly is to do the same thing, but to return all coordinates that are at least an epsilon fraction, epsilon factor times the L2 mass of the stream. That's the Euclidean norm of the vector. So it's easy to see that the L2 guarantee is in general harder. Why is that? Well, the L2 norm is always most of the L1 norm, of course, but in general can be much smaller. And when the L2 norm is much smaller than the L1 norm, then you're asking to return a much larger set of coordinates. So this is a general harder problem. Additionally, we have the actual estimation of the LP norm. So that is, of course, we can't do this exactly. There's possibilities of results to say that you can't do it exactly unless you store the entire vector. But we want to approximate it to a 1 plus or minus epsilon factor. And in addition, for p equals 0, we use the convention that the L0 norm of the vector is just the number of non-zero coordinates at the end of the stream. That's the support size. So we would want to estimate that to a 1 plus or minus epsilon multiplicative factor. And there's some other well-studied problems as well, such as LP sampling, that's returning some coordinate in the stream with probability proportional to its LP mass. Support sampling, returning some uniformly random non-zero coordinate of the stream. Entropy estimation and inner product estimation. So if I have two vectors f and g, estimate the inner product between them. Okay, so the observation that got this work started is that between the two models, the turnstile model and the insertion-only model, there is a log-in gap in the space complexity required for pretty much any problem that's been studied in the literature. Why is this? And what do I mean by this, actually? So I mean that for a lot of problems, and here's a subset of them, there is a lower bound given in the turnstile model that is a log-n factor greater than the best known upper bound in the insertion-only model, which means that in most cases there's actually also a matching lower bound in this case. So there truly is a log-n gap between the complexity in the turnstile model and the complexity of these problems in the insertion-only model. The second observation is to look and see where these lower bounds from the turnstile model come from. Why does it require another log-n factor of space? So the observation is that these streams, these lower bounds almost always come from streams that have a large number of insertions and then a large number of deletions. So I'm not going to get into too much detail from where these come from, but essentially almost all lower bounds in the turnstile model come from reductions from problems of communication complexity. So the way this works is that you have two parties, you have Alice and you have Bob, and they're both given some input. And then they want to solve some function, compute some function over their input. And so Alice is going to send some message to Bob, and then Bob's going to receive that message and output some result to solve the problem. And the goal is, of course, to have a small message size, because Alice could just send her whole input. You want the message to be small. So there are lower bounds from information theory, which show that the message must be at least of a certain size. And the way you get lower bounds to the turnstile model is reducing from such problems of communication complexity. So how does this work? Alice has some communication problem with Bob, and she creates some stream and inserts a large number of items into the stream corresponding to her input. Then at this point, the L1, as you can see, the L1 of the vector is very large. She's then going to send the state of the streaming algorithm over to Bob. Bob's going to receive it, use his input to delete off a lot of irrelevant data from the stream. And at the end, the L1 is very small. The signal is, there's no more noise in the stream. And you can use his streaming algorithm to solve the communication problem. And this is where these reductions come from. So we thought, so actually notice that this step right here where Bob deletes off the relevant data, it's very important for these lower bounds. Because if he doesn't do it, the streaming algorithm wouldn't be able to give a good approximation of the values needed to solve the communication problem. So we asked the question, what if we prevented Bob from doing this? What if we considered only streams where the number of deletions that were allowed were bounded in some sense? Could we beat these lower bounds that have been derived in the turnstile model? And the goal of this work is to answer that we indeed can do this for many problems. So we'll introduce an intermediary model which does this bounding of deletions. And I think we do it in a rather natural way. So we're going to define two vectors, the insertion vector and the deletion vector. So the insertion vector is just the vector of the stream, the underlying vector, had you only considered the positive updates. So you only consider the insertions. So it's a stream restricted to the positive updates. Similarly, the deletion vector is the same thing, but you only consider the negative updates. And then you're going to take absolute values so that they're both positive vectors. So at this point, this is just another way of writing the stream vector as the difference between two positive vectors. So then our model formally is as follows. It's not terribly complicated. So given some parameter alpha, at least one, we say that f is a bounded deletion stream, or equivalently f has the alpha property, if the sum of the L1 mass between the insertion vector and the deletion vector is at most an alpha factor times the L1 at the end of the stream. That's F1 here. So I think an easier way of thinking about this is if you assume the unit update model. So this means that all updates in the stream are either +1 or -1. Now note that this can be done without loss of any generality, because if we have a larger update, we can just implicitly assume it's many updates of +or -1, and this doesn't reflect the complexity of any of our algorithms. It's just a way of thinking about the problem. And if this is the case, then the way that what this alpha property is saying is that the L1 at the beginning, at the end of the stream, is at least a 1/alpha fraction of the length of the stream. So it's a lower bound on the L1 at the end of the stream. You can't delete off everything at the end. So I like to think about this visually. This is the best way for me to visualize it. So again, we're going to look at the graph of the L1 of the stream versus time. And so in this context, what's an insertion-only stream? Well, an insertion-only stream, there's only one graph of an insertion-only stream, right? At every time step, the L1 increases by exactly 1. So this is the only possible graph of such a stream, insertion-only stream. It's a straight line with slope 1. Now I'm going to draw another line. This black dotted line has slope 1/alpha. Now this black dotted line is going to be the lower bound for an alpha-bounded deletion stream. So an alpha-bounded alpha property stream, I think it's easier to say it that way, simply must be above this black line. It's a lower bound on that stream. It can have deletions, and note it can have the amount of deletions is not bounded by additively in alpha. It's bounded multiplicatively in alpha. And in fact, in our paper, we actually consider a more general model where this blue line here is allowed to dip below the black line at any time, as long as at the end of the stream it's above this black line. So the real restriction is at the end of the stream, the alpha property stream is above this lower bound with slope 1/alpha. And then what's a turnstile stream? Well, a turnstile stream can do whatever it wants, as long as it can go up and down and have deletions. It can't be above the insertion-only stream, of course, because that's the most L1 you could have at any time point. So the other thing I like about this graphic is that it illustrates one of the important points of this model, which is given this parameter alpha, which gives the slope of the line, if you send this parameter alpha all the way to 1, it collapses on the insertion-only slope. It becomes the insertion-only slope, right? So in that circumstance, your model with alpha equals 1 is exactly the insertion-only model. You have recovered the insertion-only model in this case. Conversely, if you set alpha to be a polynomial in n, like for instance if you set alpha to be little m plus 1, then the slope of this line goes to 0. And in that case, at point m, it's still below 1. So in this case, what you've recovered is you've recovered the full turnstile model, with the exception of streams that are entirely 0 at the end. But you can deal with those in a slightly different way. It's not entirely important. Okay, so it's a tight model that sort of fluidly links the two other models, the insertion-only and turnstile model. So what's the goal of our introducing this model? Well, we said that there's a log n gap between the complexity of the turnstile model and the insertion-only model. So what I want to do is I want to look at all these problems that we have these log n factors in the turnstile model, and I want to replace one of those extra log n factors that doesn't exist in the insertion-only model with a factor of log alpha. And so these are actually our results for all these different problems. Here I'm just going to note that the strict turnstile model is a slight restriction on the turnstile model where you require that at all points the coordinates in the vector be positive. So you're allowed to have a lot of deletions. You just can't, the coordinates have to be a positive at every time step. So this is what we do. And note that when you're in the turnstile model, that corresponds to alpha being a polynomial in n. And so the complexity is the same as the turnstile lower bound. We're not doing anything we're not allowed to do. And when alpha equals 1, which is when we have the insertion-only model, this log factor just goes away. And then we recover our complexity for the insertion-only model. So it's a nice parameterized complexity that fluidly links the two models together. So I'm going to give an example of why our model might actually be applicable in some senses. Why is it a reasonable assumption? So probably the most common usage of the turnstile streaming model is when you have two insertion-only streams and you want to measure some statistics of their difference. So for instance here, suppose we have an IP network, a very large IP network, that's routing traffic through two distinct routers, F and G. And here, the ith coordinate of each of them is going to represent the number of packets sent out by, say, some IP address I. And so we want to estimate this traffic imbalance. Like, there's some load balancing we perhaps want to do, and we want to estimate the imbalance of between these two routers, of traffic between these two routers. So in this setting, the alpha property simply means that the size of the imbalance, the size of this load balancing that needs to be done, is proportional to the total traffic. So if I increase the total traffic by some factor, then the traffic imbalance is going to increase proportionally. So anytime we have this sort of statement, we have the alpha property. It's just a proportionality constraint. And so the claim is that even for relatively large proportionality constants alpha, like say like 1 over 1,000, you're still much larger and you're still much smaller than the universe size, what n is. So note that here the 2 to the 128 is the theoretical IPv6 universe size. In reality, there's not that many IP addresses, of course, but still the number of active IP addresses is very large, and we expect in many cases that alpha would be much smaller as a proportionality constant. So there's a lot of algorithms in this paper. I'm sure I could talk more about it in the poster session if you're interested, but I don't think, I can't go into detail of all the little techniques that used in each one of them, but there's some underlying ideas and techniques that allow us to gain these improvements, and I'm going to try to just describe those as briefly as possible. So the first observation is that when you have a bounded deletion stream, sampling preserves the L1 of such a stream up to L1 error. And I'm going to explain what I mean by that. So the observation is that sampling from a bounded deletion stream is like sampling from a bias coin. So imagine the following. I give you some bias coin, and I give you the promise that the bias of this coin is at least 1 over alpha. And I want you to recover the true bias. Why are you interested in the true bias? Well, the true bias is the true bias between the number of heads and the number of tails. Here, a head is like an insertion, and a tail is like a deletion. So when I know that true bias, I know the difference in some sense, and then I've recovered the actual L1 that I want to recover. So if I tell you a lower bound on this bias size, you can sample a poly 1 over poly alpha. In fact, you need only alpha squared samples. This is just a Chernoff bound to show that that's enough samples to recover the true bias. So using sampling, we can recover the L1. The second observation is that every single turnstile algorithm, and this is true in a certain strong sense, is of the following form. It picks a matrix S, a wide, fat matrix S from a randomized family of matrices, and then as the stream proceeds, it multiplies the frequency vector F by S. And note that because S is wide and fat, the number of rows is only k, and so the sketch A that you have at the end is small. It's only k-dimensional. So each AI takes log n bits to store, of course. So the total space usage of such an algorithm is k log n. So what we're going to do, one of the main technical ideas behind all our L1 algorithms is we're going to replace these counters AI with approximate counters A tilde I. And the reason we do that is these approximate counters are going to be obtained through sampling. And so if we only sample polynomial in alpha, many samples, then we've reduced the space complexity from log n to log alpha. And that's the primary underlying reason why we get this improvement from log n to log alpha. So I'm just going to briefly just put up the bound we get for L1 preservation. This isn't, it's not terribly important. It's just a Chernoff bound at the end of the day. So what do I mean by sampling preserves L1? Well, look at each coordinate and look at the positive updates, look at the negative updates, define indicator variables for whether or not we sample one of them. And then you see if you just sample a polynomial in epsilon log n and alpha, many samples and expectation, then what you're going to get is you're going to get an approximation which approximate the true value up to an additive epsilon times the number of insertions plus the number of deletions made to the item. Now note that that quantity, of course, is at most the length of the entire stream. And by the alpha property, the length of the entire stream is the most alpha times the L1. And then scaling by enough epsilons, we get the right bound. So in general, if I sample enough polynomial in alpha, log n, and 1 over epsilon, I get a frequency vector after rescaling by 1 over the sampling probability, of course, that estimates every coordinate with higher probability up to an additive epsilon times the L1 error. OK, so I'm going to come back to what the technique of approximate counters. So recall nearly all turnstile algorithms do the following. They multiply by some large fat matrix S for some randomized family. Now note, importantly, they don't actually store the whole matrix S. This is done in some tricky way so that you don't need to store the whole matrix. And this can be done linearly throughout the stream. If I got to update a 5 to the ith coordinate of F, I just find the ith column of S, and then I just add the ith column of S times 5 to A. So I don't need to do any computation beforehand. This can be done in the stream. So different families of S solve different streaming problems. In particular, the count sketch family of matrices famously solves the heavy hitters problem, and it's also been used to solve the L1 sampling problem. And a matrix of dense Cauchy IID random variables has been used to solve the L1 estimation problem. So what we do is we just want to estimate these counters AI. So we break them up into positive and negative parts, and we periodically throughout the stream, as the stream doubles, we replace them with binomial random variables with some sampling probability, and then we decrease the sampling probability as the stream gets larger. Of course, we need to do this because we don't know how to sample uniformly beforehand because we don't know the length of the stream. So this allows us to simulate sampling uniformly throughout the stream when we don't know the length a priori. And then one of the results for each of the streaming algorithms that we have is that for many families of nice random matrices S, the stream AI, when considered to be a stream on just one item, just n equals 1, that stream has the alpha property with high probability for all I for these nice families of matrices. Given that, we know that our sample approximation, A tilde, is going to be a good approximation of A up to additive epsilon AI error, just because of our results on the last slide. So given this, we have this bound here, which is just what I just said. We have a good approximation of what AI would have been had we run the whole turnstile algorithm. And then given that, we're able to show that for algorithms who don't take the output and blow it up by some crazy constant, what you've done is the output of your algorithm given your approximate sketch A tilde is going to be a 1 plus or minus epsilon approximation of the output given A. And this is how you obtain the results for these L1 problems. So I have a couple minutes. I'm going to briefly talk about L0 algorithms. So L0 algorithms constitute support sampling and, for instance, just estimating the L0. So it doesn't actually make sense to sample to solve problems in this domain because sampling doesn't preserve the properties that you want here. And in fact, you kind of need a different notion of alpha property to solve problems in this domain because the earlier notion didn't make sense. So we're going to define a more general notion which lower bounds the L0 norm. Recall that's the number of that's the support size of the stream at the end of the stream by a 1 over alpha fraction times the total number of items that have been seen in the stream. That means the total number of items that at some point in the stream were non-zero. So given this, we note the following. Many turnstile L0 algorithms do the following thing. They create log n substreams corresponding to log n levels of subsampling. Where each level of subsampling, you have an expected n over 2 to the I coordinates remaining. So what they do is they run a data structure on every single one of these streams, and then at the end of the stream, they find the substream that corresponds to a guess, so that the L0 approximately there's a constant number of non-zero coordinates in that substream. And then they use their data structure to solve the problem. The issue is, of course, that the L0 can be anything. It can be anywhere from 1 to n, so you need to remember all the substreams. And then the observation is that if you have the alpha property, it immediately follows that if the L0 is equal to L at some time step, then it'll never drop below 1 over alpha, L over alpha, anytime in the future. So we use this result to say, maybe for alpha property streams, we only need to remember those values of the L0 for which it could possibly be that value anywhere in the stream. And this is how, roughly, we get our reduction from log n to log alpha. And these are our results, again, for the problems you can consider. And I'm happy to talk about it more offline. Thank you.
Something about the model. So does it really matter if the gap is more than A at the end or throughout the...
Yeah, so I mentioned that briefly. So in the illustration, it showed it all being above it, but that I think is just for clarity. In reality, all that matters is at the end that it's above the value of the gap, because really what's going on is that you're not querying it any time until the end of the stream. So at the time of query, whenever you're actually querying it, it needs to be above the line. That's the only restriction that's required.
Question. So as far as I understand, you need to know in advance the alpha for your algorithm, right?
Yeah, so
can you do something better to be adaptive to the alpha? Depending on the alpha of the streams, your algorithm adapt to the...
So, I mean, we haven't actually considered that a little bit. There's nothing like that in the paper because, so for one instance, you could guess values of alpha, but then you've lost the bounds you have. I don't know about adaptive algorithms. That's a good idea, but I think in general adaptivity doesn't work because this sort of bound can change at any time in the stream. I can be doing well, and then at the end of the stream I can just delete everything off. Okay. You know, so you can't really guess beforehand. Like a turnstile stream can go up and down and up and down. There's no way to really predict what the value of alpha is going to be at the end, unfortunately.
Okay. Thanks.